Thank you everyone for watching. Today I'm going to present the result of a research I have made at the final project for the numerical method subject on the National University of Colombia, titled Predicting the Weight Gain on an 8-month female baby with Parametric Regression. She's my baby Amelie, the main subject of this study. Well, the WHO charts are charts created by the World Health Organization to provide an outline of how babies should grow. A percentile represents the position, given that all data is sorted, and what it tells is that if a baby weight is on the 75 percentile, it means that between 100 babies, 75 of them will weigh less than the current baby, and 25 of them will weigh more. Usually, the World Health Organization tells that a normal baby growth is achieved when it moves slowly between percentiles, usually up, and a sudden drastic change on percentiles will mean an abnormal under or overgrowth, which should be consulted by the pediatrician. The purpose of this subject is to provide a predictive approach, since all the tools that were found are basically for the current information. This means that a baby which have abnormal growth can only be detected when it have reached a critical value on the percentiles. This research aims to provide a tool that can make predictions. Given that no data was found on a large scale that could train a model between months, the predictive model goal was set to 15 days. So what we wanted was to make a parametric model that take 15 days of data and provide the next 15 days of weight. The main difference between parametric and non-parametric regression is that on parametric regression we are assuming that a finite amount of parameters models completely the data, and on non-parametric regression we need a larger amount of data so that the algorithm can detect the model that best fits the data and also train. In this research, we use parametric regression. Here we can see the data collected. These are the 15 days of measures used to train the models, and we can see here that the behavior is usually non-linear. So what we see is that we have a big growth at first days, then it decays and maintains equal. Again, it grows, maintains equal, and it grows and maintains equals. This is clearly a non-linear model, but what we expect is that we can predict the average outcome of the weight, so that with these 15 days of data, we can predict the final weight at the month, at the 30 day, and predict in which percentile will the baby be. If the baby jumps to a much higher percentile or jumps to a much lower percentile, we will have 15 days to go to see a pediatrician, hence providing an early alarm. Well, we use the MATLAB curve fitting, which is a tool of MATLAB that can provide optimization for different kinds of curves, and this allows us to quickly navigate through different models. It is important to highlight that in this research, all models provide a height and close to 1 R² value. This means that it makes a good fit of the data, and make a small residual sum of squares, which is the error between the predictive outcome and the real data. So these statistical measures didn't allow us to decide which one was the best method, so we make another 5 conditions, which are that the weight should have a faster growth at the first days, as we see on the previous slides, and it should be decaying as days pass. It should be as close as possible to the first 15 points. It should predict data correctly at first. No discontinuities. The difference between the value at day 1 and at day 30 should not exceed 1 kilogram, because we can derive this data from the WHO charts. It is not an expected gain weight, and it should not swing or oscillate strongly. Well, these are the first discarded models. All the polynomials from the first degree to the 6th degree provide a behavior that did not satisfy the previous condition. It oscillated too much, it predicted too much high of a value. We expected that the square function could somehow model the data, since it should sort of fits the model, but when it gets optimized, the best result was this line, which also predicts a much higher value. The two working models that we find was the power model and the saturation power model. Also, this second degree rational model, which is a constant divided by a second degree polynomial, and the difference between these three models are the final value outcome. So, in order to get the exact parameters of our models, we replicate the results of the MATLAB curve of optimization with our octave. We test the linear regression, we use the normal equation, and also the least square approach using the f-min search function of octave. It is a curious data to highlight that no difference were found between applying linear regression after linearizing our relationship and between directly minimizing the list of squares. We also, in order to provide a nonlinear complex processing, use the neural network fitting tool of MATLAB. We test various different neural networks, and the best one is highlighted here in orange. The blue points are all the data points. Although the neural network was trained only on these 15 days. We can see a strange coincidence, which is that the neural network made a steady prediction after the 15th day, and this steady prediction, this constant behavior, actually predicts the final weight correctly, but this behavior here was unexpected, and further adjustment of the architecture, the algorithm, and the number of layers should be made in order to test if neural networks had a good approach to model this data. The final data and the fittest model we'll find was with the power model. All the other models provide a much higher value or a much lower value. The saturated power model predicted a much lower value, and the second degree rational model predicted a much higher value. The data, the final 15-day data can be found here, and the difference between the predicted value of the model and the measured data can be found here. We can see excellent behavior, both in prediction and minimizing error, and in overall behavior of the model. It is important to highlight that the biggest errors occur in these steps, where no change on weight is found, because the model cannot model a steady behavior. It always keeps growing. So here at these steady points of the data are the biggest errors. Further research has to be taken for many reasons. First, we need to know if the model that we use, the power model that worked so well to predict the data from the 8th month to the 9th month, if only applicable to my baby Amelie or to other babies, or even if I could apply it the next month. Because what we can see here is that I choose the fittest model based on the final predicting outcome. But it has to be checked, it has to be researched if this can be made with other children and in other months. Maybe it worked only for the 8th to 9th month on Amelie. Also, the parameters of the model, the A and B parameters, could have a biological meaning, and it could be used to detect growth anomalies, but have to be researched. It will be useful to test if other growth indicators could be modeled the same way as was made here. The neural network approach as a non-linear complex function could have many potential to make a good model of this behavior, but have to be further researched. And a neural network or a more complex non-parametric regression could be used to fit a larger amount of independent variables. For example, here we use it only day to predict the weight, but there are several values, several parameters that can affect the weight of a baby, like sleep patterns, the number of meals, the weight of the mother, the weight of birth, and so on. Thank you for watching.